So we know lattice energy is the energy you'd have to put in to break up the attractions in an ionic solid. So if you had a specific quantity of ionic solid, you have a specific number of positives and negatives, and they're all lined up, and they're all surrounding each other to maximize their attraction, so that continues in all directions, and three-dimensionally, so we get this large kind of cube of positives and negatives that are all organized to maximize their attractions. So the lattice energy is the energy absorbed to break those attractions. In a solid. Anytime you break attractions, you have to absorb energy. Anytime you form attractions, you release energy. Right? Because to break attractions, when the attractions are there, there's not much potential for it to undergo change on its own. It can't change on its own. We have to put potential energy in if we want to get it to a higher potential energy state where the attractions are broken and now they have a higher potential to bring their attractions back together. So the factors that affect that, the biggest factor is the quantity of charge. So the more charge we have, the higher the lattice energy. So if you have ions with a +2 attracting to a -1, that should have probably more lattice energy than something with a +1 and a -1. Or if you had something with a +2 and a -2, that's going to have even more lattice energy. So the more charge you put on the individual ions, the more strongly they'll be attracted, the more energy it will require to overcome that attraction, which means you have a higher lattice energy. So if you're given a bunch of examples, you'd have to analyze what's the formal quantity of charge on each one of the ions that's attracting. Usually if they have more charge, they should have more lattice energy. And then the other thing is the ability to pack the ions closely in the lattice. So the lattice is just a way of saying the organized structure that these ions are packed into. So if I can pack them closely, then it will have also a higher lattice energy. And that's not always easy to predict, because you have these charged particles. You know, if the particles are all really large, or if they're similar in size, it's going to be hard to pack them closely without leaving small gaps between them. If you have, one large one and a small one, the small ones can sometimes pack nicely into the gaps around the larger ones. So I'm not going to expect you to really predict necessarily whether one specific compound will be able to pack better than another specific compound. But you should know that the ability for them to pack closely does improve the lattice energy. It makes the lattice stronger, and it means more energy is required to break those attractions. And it also means that the solubility of that will be less in water. Right? So if the stronger the attractions are between the particles in the solid, the less likely they are to get dissolved and break some of those attractions and get surrounded by solvent molecules if you dissolve it. So lattice energy is useful. It tells us about some of the properties of these substances, which we'll talk more about later in the semester and also in general chemistry too.